Here we have a Jee Advanced 2024 question from Dual Nature of Radiation. It's a PYQ of Jee Advanced, and in this question we are asked that a metal target with atomic number Z is equal to 46 is bombarded with a high energy electron beam. The emission of X-rays from the target is analyzed. The ratio R of the wavelengths of the K-alpha line and the cut-off is found to be R equal to 2. If the same electron beam bombards another metal target with Z equal to 41, the value of R will be. So for this question, first of all, we will consider a metal surface. This is a metal surface in which the atomic number, that is Z, given is 46. It is bombarded with an electron beam, and after bombarding it with electron beam, it emits the X-rays. So after the emission of X-ray, what will happen? It's given that its atomic number 46 bombarded with a high energy electron beam, emission of X-ray, and ratio R. R is the ratio of wavelength of K alpha equal to lambda K alpha, that is wavelength of K alpha line and cut off is found to be R equal to 2. Now we have and again another case is given in which the same electron beam is bombarded on another metal target with Z equal to 41. So here is our another metal target in which Z is equal to 41, and it is bombarded again with electron beams, and that is the same electron beam. And remember one thing, that if these two electron beams are same, then their cutoff wavelength will be same. As these electron beams are same, therefore their cutoff wavelength will be same, because in the question it's given that the electron beam is same for both conditions, and again it will also emit the X-rays. And for this question we have to calculate what is R. For here we can let that R is equal to R1, and for here we can let that R is equal to R2, and lambda K alpha let it be 1, and here lambda K alpha 2 divided by lambda cut off is equal to question mark. We have to find this one. Now see one thing, that when you see that the ratio of wavelength of K alpha, when you see the K alpha line, then remember that it is the condition of characteristic X-ray. There are two types of X-rays, and out of that one type is the characteristic type, and here it is given K, that is here K is equal to K shell, that is the K orbit, and K orbit means n equal to 1, and alpha here means that when an electron from K shell or the K orbit will go away or will jump off from the K shell, then another electron from L shell, that is the n equal to 2 shell, will jump to take its place and fill the vacancy. That is, for K alpha, the K indicates n equal to 1, and alpha indicates n equal to 2 to n equal to 1. The electron will jump from the second orbit to first orbit to fill the vacancy that is caused by the first electron present in the first orbit. And for characteristic X-rays, there is a simple formula that was given by Mosley, and it is also called the Mosley equation, that is En, that is the energy, is equal to minus 13.6 Z minus 1 square by n square electron volt. It is the Mosley's equation for characteristic X-rays. And from here we can see that you see that En, and what is En? We know that E is equal to hc by lambda. We know E is equal to hc by lambda. So from here we can write that you can see that lambda is in the denominator and z minus 1 is in the numerator. And again see n square, what will be here? N square will be the change in the uh, orbit, that is the change in the orbit, that is from n is equal to 2 to n is equal to 1, there is an electron jump, so it is also constant. It is also constant, and when you see hc, that is also constant. So from here we can write that lambda is inversely proportional to z minus 1 whole square. So from here we get that lambda is inversely proportional to z minus 1 whole square. And do you know that why we have taken z minus 1? Because when we write z minus 1, then here 1 is the screening constant. Because for the k shell, we see that sigma, that is the screening constant, its value is 1. And as a result, for here we have also written sigma is equal to 1 and written directly z minus 1, because according to Moseley's equation, root over of frequency is directly proportional to z minus 1. It was the Moseley's equation, and from here we get that sorry from here we get that frequency is directly proportional to z minus 1 whole square. And from here we get that uh, we know that E is equal to hc by lambda is equal to h nu, that is lambda is inversely proportional to 1 by z minus 1 square. So we can also directly write this formula that lambda is inversely proportional to z minus 1 whole square. And after this, what we have to do is see that we have got this one, lambda is inversely proportional to z minus 1 whole square. Now see, for this case, for the case of r1, for one number case, for r1 you can see that lambda k alpha 1, lambda k alpha 1 is equal to 2 times lambda cut off, and we can write it that it is directly proportional to 1 by z minus 1 square. So we are adding one constant, that is k. So if we add another constant called k here, then it becomes k times z minus 1 whole square. And for one number z was given 46, so it will become 46 minus 1 whole square, that is 45 square. So we have got one equation here, that 2 times lambda cutoff is equal to k by 45 whole square. And from here we will get that k is equal to 2 times 45 square into lambda cutoff. And for the second case, it is the first case, and for the second case we see that lambda k alpha is inversely proportional to 1 by z minus 1 square, that is we can see that z was here 41, so 41 minus 1 is 40 square. And from here we can write that you can again replace it with k, because the constant will be same, there will be no change in constant for the same electron beam. So here we can write lambda k alpha is equal to k by 40 square. And here we knew that already that k is equal to 2 into 45 square into lambda cutoff, that is k is equal to 2 into 45 square into lambda cutoff divided by 40 square. And again if we simplify it, then you see that what we have to find, r2 is lambda k alpha 2 by lambda cutoff, that is r2 is equal to lambda k alpha 2 by lambda cutoff is here equal to 2 into 45 square, that is 45 into 45 into lambda cutoff divided by 40 square, that is 40 into 40 into again lambda cutoff. So lambda cutoff cuts the lambda cutoff, and from here 2, 20 is a 40, 5, 9 is a 45, 5 4 is a 25, 9 is a 45, 5, 8 is a 40, that is 81 by 32, and 81 by 32 is equal to 2.53125. so this is our final answer. This will become our final ratio, 2.53125. so 2.53, that is option number A here, becomes our correct option. And here we have solved the Jee Advanced 2024 paper 2 online question of dual nature of radiation.